Hi everybody, hope everybody's doing okay. We are, and now this is our third lesson since of new stuff since school's been closed. Getting ever so closer to that AP test. I just got an email today. It looks like they'll be taking that a little bit later than you normally would have. I think we were scheduled for May 7th. Email I got today said that all tests will be taken between the 11th and the 20th. So it gives us a couple extra days, gives you a couple extra days, and gives between us probably about an extra week to get ready for that roughly. So today what we're going to talk about is simple harmonic motion. Today really shouldn't be too bad. It's not a crazy idea, and the math is pretty straightforward. So let's get right to it. So simple harmonic motion is just the back and forth motion exhibited by a pendulum. Something like this, a ball on a string, it's hanging straight down, you push it off to the side, and then you let it go back and forth. And actually, I have a GIF of one of these that is right here. You see it's just going back and forth, back and forth. And we see this all the time in our childhood, right? Every time you go to the playground and you get on the swing set and you swing on the swing, this is exactly what you're doing. You're exhibiting simple harmonic motion when you swing on a swing set. Okay, so nothing too complicated. It's a big old name, the whole simple harmonic motion, but not complicated. It's just regular back and forth motion like a pendulum or a swing, just like this. All right. Now, that's not the only place that we see simple harmonic motion. Another place that we see simple harmonic motion is with springs. So if you've got a box here, you've got a spring attached to the wall, you push the box up against the spring, and as long as they're attached, so like the box just doesn't go flying, these things would have to be attached. You can push on the box, and the spring is going to push it back out, and it's going to go past where it just it's going to go past where it likes to rest because it's pushing, 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 and it's not going to stop pushing just because it hits the middle. It's going to keep pushing, and then it's like, oops, I went too far, so I want to pull you back. And if you're having trouble visualizing that, here we've got this over here. Okay, so here, that's exactly what I've got. This one is hung vertically instead of being horizontally on the ground, but it still works the same. Okay, so this green line is where this is starting. And if I raise the pendulum up to this red line, let's watch what happens. Okay, it falls, and notice it falls past the green line, right? So it falls, and then it gets past where it was just hanging out, and it falls farther, and then the spring's like, oh, nope, I want you back, and so it pulls it back up, but it pulls too hard, it goes back up, all the way back up to the red line, and it just keeps going back and forth, back and forth. And so, not a pendulum, but it is a regular back and forth motion. We can measure how long does it take to go back and forth, how many times does it go back and forth in a minute. Those are all things that we can measure, which which does make it simple harmonic motion. It's back and forth. Okay. So let's review a little bit. We have talked about something called period before, back when we did waves, and I just want to remind everybody what that is. So anytime that something shows cyclical behavior, and also cyclical behavior means is that it goes through repeated cycles. And so anything that goes through a cycle, back and forth, or even in a circle, right? A circle counts as a cycle. The engine in a car, that does cycles. It goes around in circles, and so you can count how many times does the engine, how many cycles does it do in a minute, and you actually have a gauge in that for that in your car, right? That's your RPMs. RPM stands for revolutions per minute. It's counting how many cycles your engine goes through in 1 minute. Okay, so anytime that we had cyclical behavior, just something, anytime something goes through repeated cycles. Okay, usually when we have something like this, someone is usually interested in the amount of time it takes to complete exactly one cycle. So I just mentioned car engines. For example, if you're the person designing that engine, you're going to care about how long it takes to do one cycle. Okay, that type of thing. All right, the amount of time needed for exactly one full cycle is called the period. Okay, so one time around. So, or if you're on the pendulum, or if you're on the swing set, that's back and forth is one full cycle. And I wanted to emphasize that here. So for the pendulum, a cycle, and for the spring too, one cycle is back and forth. So if the pendulum starts on the left, a full cycle falls through to the right side and returns to the left side. So it's not from the left side to the right side. That's not a full cycle. A full cycle would start on the left side, go to the right, and then come back to where it started on the left side. That is one full cycle. And measuring in the time that it takes for one full cycle, that has a name, that's called the period. And that's what we're focusing on today. How long does it take to do one cycle? Okay, so for a pendulum, here I'm just going to go ahead and give you the formula. Here it is. T is the period, equals 2 pi square root, and then inside the square root we have this L over G. So T is the period, L is the string length, so it's how long is this string right here from the ceiling down to the little red ball. How long is that string? That's what L is. Okay, and G is the acceleration due to gravity. So as always, that's going to be 9.8 on Earth, like we've been using for a while now. But on different planets, it's a different number. That's 9.8 is just for Earth, so it's important to put there. And if you have another planet, they should be giving you the G so that you can use it. Okay, so we want to notice a couple things about this equation. We don't just want to be able to plug in and just calculate numbers like a calculator. Okay, we want to notice things. So L is in the top here, right? So that means that if we make the string longer, if we were to make that string longer, then that means it's going to take more time to go back and forth. L is in the top, so if you make L bigger, that means T for time is going to be bigger. So the time to go back and forth is more for a long string than it is for a short string, okay? The other thing is, if you look at G, where's G? G is on the bottom. So if you move to a planet that has a stronger gravity, that's actually going to make your T smaller, right? If you get a bigger number in the bottom, that's going to make the period smaller. So more gravity would actually mean that it takes less time to do back and forth. One thing that's interesting, right, is that when it comes to the pendulum, there's no mass up here. There's no M, right? So mass does not matter. You and someone, if you go to the park and you two want to swing next to each other, it doesn't matter if you're the same weight or not. As long as you start in the same spot and your swings are the same length, then you should be able to stay in sync. The only thing that really matters is how long the chain is or how long the string is, whatever you're using to hang something. That is the only thing that matters. Well, on gravity too, but on Earth, gravity stays the same. So as long as you're staying on Earth, the only thing that you can change to change the amount of time is the length of the string. Kind of interesting. Mass does not matter. All right. For a spring oscillator, I'm going to give you the equation here again, and it looks very similar. The T equals 2 pi, and then we have the square root with a fraction inside of it. But this time, the letters inside the square root are a little bit different. Instead of L and G, this time we've got M divided by K. Okay, just like before, T is the period. T is how long it takes to go back and forth. M is the mass this time, so this time mass does matter when we're talking about a spring oscillator. Okay, and K is the spring constant. All right, and we used that a little bit before with the potential when we were doing energy. You should be familiar with that K. Again, we want to kind of dig into this equation just a little bit, not just plug in and do numbers, but notice that M is on top, right? So the more mass that your box has right here, that means that if you increase that mass, that means it's going to take more time to do your back and forth motion. Okay, so more mass means a longer period, more time to go back and forth. But K is on the bottom. Okay, so that means if you have a spring with a higher spring constant, on a higher spring constant, that means you're making your spring more stiff. The bigger your K is, the more stiff your spring is. If your K is really, really small, then it's kind of like a slinky, and you can just open it and close it, and it doesn't feel like much at all. So bigger K is a stiff spring, and because it's in the bottom, if the more stiff that your spring is, that's actually going to make it take less time to go back and forth. So a bigger K means because it's in the bottom, means a smaller T. So if you're designing something that uses springs like this, and you're noticing, wow, it's taking a really long time to go back and forth, that means you need a stiffer spring. The more stiff your spring is, that means you have a bigger K, and you'll make the period smaller. Okay, and that's really it. This week doesn't have a whole lot. That is it. Your homework is actually on Brain Genie. It's only two small goals, and it's pretty much plug and chug with those two equations I just gave you. So you also want to make sure, just in case, that you're comfortable finding either like G or finding K or finding M or L. So what I would do if I was you is I would solve each one of those equations so that you can get yourself a formula for those things. Just to give yourself some practice with the algebra, keeping yourself sharp on your algebra skills, making sure that you can solve for those other variables. All right. Hope everybody has a good rest of your day, and we'll talk to you next time.